Okay, so we are going to start 6.1 on slope fields. Actually, slope fields is one part of the section. The other part are these differential equations. So, a differential equation, and when we solve these differential equations, basically we're going to start with dy dx. And then we're going to figure out, we're going to solve y equals and then some equation. So this equation is our solution. We're going to look at a little bit of different terminology here. In example one, it says find all functions y that satisfy dy dx. And this one says find the general solution. They both mean the same thing. They basically say we want to get y equals, right? And then we're going to have some function, and then we're going to have a plus c at the end. And same thing for this one. Whenever it says general solution, we're going to have a plus c. So this is what we're going to do. We are going to start with moving the dx to the other side. So as if we're going to multiply both sides by dx. So it's going to look like this. Secant squared of x plus 2x plus 5 dx. Now the only way we can get rid of the dy and the dx is actually to integrate. So we're going to integrate both sides. Now the next part is going to look like what we've been working with. So I'm going to do the right side first. We're going to have integral of secant squared, that's tangent of x, plus, and then we're going to have 2x squared over 2, or just x squared. And we have plus 5x, and then we're going to have plus c since there are no bounds. Now what we haven't done before is looking at the left side. Now the integral of just dy. Think of, remember when we had something like, 1 plus u du when we did integration, u substitution. So basically that 1 became a u because of the du, and then we would have u squared over 2, and then we'd have our plus c. So think of this the same way. We are integrating, that's really a 1 dy. So I take whatever variable that is, in this case, y. So I'm going to end up with a y here. Now technically there's a plus c on both sides, but keep in mind these plus c's are not necessarily the same thing. So I want to just make sure that I get my variable on both sides, or I'm sorry, I get my constant on one side. I'm solving for y equals. So I have tangent of x plus x squared plus 5x. Now c1 minus c2 is still just going to be some constant. So when we solve for this, we're always going to have the plus c on the right side of the equation. Just makes it easier. Plus we want to have it in the form of y equals and then whatever our function is going to be. Okay, find the general solution. So first thing we're going to do, again, we're going to have dx moved to the right side. And now we want to integrate. So I end up with y equals secant x, tangent x, the integral of that is secant. Again, this is one that you don't need to memorize, but you may encounter. Now e to the x, the integral of e to the x is e to the x, and then we put our plus c here. Again, you're probably asking yourselves, didn't we already do this? Yes, we did this, but that was when I gave it to you in this format where I set up the integral for you. There's a reason we have to do these types of problems, and that is when we have both x and y involved in our derivative, which we will see eventually. But right now I just want to get you used to the process. So same thing here. I'm going to have dy equals, I'm going to write 1 over x. I'm going to rewrite x, 1 over x squared is x to the negative 2 dx. So we're going to integrate. So I get y equals, and it's going to be ln of absolute value of x minus x to the negative 1 over negative 1, and then we have a plus c. So we have y equals, now the absolute value I can drop mainly because it says right there x has to be greater than 0. So I have ln of x, and then that's going to become a plus 1 over x plus c. Okay, let's continue here. So I have dy equals cosine of t e to the sine t dt. I'm going to put my integral sign on both sides. Remember, it's just like balancing the equation. Whatever I do to one side, I have to do to the other side. So here I get y equals. Now, I want to integrate this, but I'm going to have to do a little u substitution here. So I'm going to let u equal sine t, and du then is going to be cosine of t dt, which I happen to have here and here. So I'm going to rewrite this as e to the u du. And here I get e to the u plus c. And we want to go back to what u is originally equal to, which was sine. So e to the sine t plus c. Now we want to take it to the next step, which is now we want to find the initial value problem. We might also see this as finding the particular solution. So this is given a particular point. Okay. It's called initial value. Usually you have an initial value like when x equals 0, y equals 4, but it can be any point. And here is the process for that. So first thing is going to look just like the previous problem. So I got e to the x minus 6x squared, and we're going to move the dx over to the right side. Okay, don't worry about this. It's just find the particular solution whose graph passes through the point 1, 0. So I want to integrate both sides. So I still get my y equals. Here I'm going to get e to the x. Then this will be minus 6x cubed over 3, or minus 2x cubed. And we still have our plus c. Okay, so step 1 is we integrate. Step 2, here's what we want to do. We're going to use this. So we're going to plug in 1, 0 and solve for c. Okay, so right here, x is 1, y is 0, so I have 0 equals e to the first minus 2 times 1 cubed plus c. So I get e minus 2 plus c, or 2 minus e is equal to c. Okay, and then finally, we want to rewrite our solution with c. So in other words, I'm going to take this and plug it in here. So I have y equals e to the x minus 2x cubed plus 2 minus e, which was our c. Okay, solve the initial value problem explicitly. Same thing, again, it says solve the initial value. So we are going to start out with dA. We have 10x to the 9th plus 5x to the 4th minus 2x plus 4 dx. So I want to integrate both sides. Now this one says dA, so I have a equals, this is going to be 10x to the 10th over 10 plus 5x to the 5th over 5 minus 2x squared over 2 plus 4x, and don't forget our plus c. Of course, this works out really nicely. We can see our coefficients cancel out in those situations. And now I want to plug in a equals 6 when x equals 1. So I have 6 equals, well, 1, 2, right? 1 to the 10th is 1. 1 to the 5th is 1. 1. 4 times 1 is 4, plus c. So c is 1. Okay. Now we go back. A equals x to the 10th plus x to the 5th minus x squared plus 4x, oops, not plus c, plus 1. Okay, so we have 2 more examples here before we get to slope fields. So the first thing we want to rewrite this. I'm going to write this as x to the 1/2. Again, we do this because anytime it's a power other than x to the -1, which is 1 over x, it's helpful to write it with the numerical notation. So here we have y equals 5 is just a coefficient. Antiderivative for secant squared is tangent. Okay, now x to the 1/2 becomes x to the 3/2 over 3/2 plus c, and we'll notice those will cancel out. I'm going to plug in y equals 3 and 0 for x. So basically we get c is 3 because tangent of 0 is 0. So I have y equals 5 tangent of x minus x to the 3/2 plus, not plus c, plus 3. All right, dy equals cosine x dx, integrate, we get y equals, it is going to be sine of x plus c. So this is just a slightly different notation. We got x is 0, y is 1, sine of 0 is 0, so c equals 1. So y equals sine x plus 1. Okay, next we have slope fields. And in the following lesson, we're going to see how these two pieces come together with differential equations and slope fields. So derivatives can be defined in terms of x and y. We saw this actually back when we did implicit differentiation. So in order to draw a slope field, we're going to make small line segments. So let me give you an example. Let's say we have a slope of 1. So let's say there's a point here and I want to draw a little line segment with a slope of 1. So that would be approximately a slope of 1. When I draw these, I think, okay, the amount I go up and over should be like up 1 over 1. It should be the same distance. What would happen if I had a slope of 2? Let's say I have, here's my point and I want to make a slope of 2. So this time I'm picturing, again, these, you're going to notice when I do these, it's going to be a real rough sketch. So here I'm going up, right, going up 2 and over 1. And you'll see this line has a steeper slope than the one before it. Let's say it's a slope of 1/2. So now I'm going to go, right, picture up 1 over 2. So again, you're going to just estimate, and you see that this is more horizontal than the two above. So here's what we're going to do. We have all these points that are set up, and here is our differential equation. So we're basically thinking about what would each of the slopes be at these points. So let's start with, I'm just going to write out a couple of these. You don't have to do it for every point. I'm just going to show you. Let's start with this point here at 1, 2. Okay, at 1, 2, I have, it's going to be 1 over 2 because it's x over y. So here, I'm going to try to make a little slope field. You don't want to make the line segments too long, okay, because you don't want them to intersect with each other. Let's look at the one right below that at 1, 1. So dy dx at 1, 1 is going to be 1 over 1. Okay. So that's about, again, you want to try to picture, like if I were to make a triangle, you'd kind of want to make like an isosceles right triangle there. It doesn't have to be perfect. You just want to look at, this one has to be less steep, or I'm sorry, more steep than the one above it. Now the next one, let's go with the next one below that. Let's say 1, 0. Well, what happens in this situation? I get 1 over 0, which is undefined, right? So that would normally look like a vertical line, but we're going to leave these blank. In fact, all of these at -1, 0, 0, 0, and 1, 0, we're going to leave these blank because these are all undefined. All right. Now, what happens at 0, 2? Well, at 0, 2, I'm going to have 0 over 2, which is 0. So actually, we get a horizontal slope here. Same thing at 0, 1. That's going to be 0 over 1, which is 0. Then down here at -1, 0, -1, I'm also going to get 0. Let's go down here, 1, -1. That's going to be 1 over -1, which is -1. So there's my slope of -1. Let's go to -1, 2. This is going to end up being a slope of -1/2, so something like that. At -1, 1, I'm going to have a slope of -1, so that's going to be like that. Again, that one we're going to leave blank. And then -1, -1, -1 over -1 is 1. So that's going to have a slope of +1. So it has a little bit of symmetry there. Okay, next one, dy dx equals x plus y. So now we're adding the x and the y coordinate. So let's say we start from -1, 2 this time. So -1 plus 2 is 1. So that's the slope of 1. Next one is -1, 1. So we add those. We're going to have a slope of 0. -1, 0 is going to have a slope of -1. And -1, -1 is going to have a slope of -2. So that's going to get steeper, but in a negative direction. Here, at 0, 2, it's going to be 2. At 0, 1, it's going to be 1. Remember, I'm just adding. I'm just adding the x and the y coordinate. 0, 0, well, that's going to be 0. 0, -1 is going to be -1. Up here at 1, 2, I'm going to have a slope of 3, so that's going to be pretty steep. 1, 1, I'm going to have a slope of 2, a little less steep. 1, 0 is a slope of 1. And 1, -1, add those together, we get 0. And that is it.